So just an indication for next week. So there won't be classes on Wednesday because I am in a busy research trip, let's say. And um, so we won't have classes on Wednesday. On Friday, instead, you will have a first session about the project. So Sebastian Troia, who is the person who is helping us with the project, will come and start explaining you the framework, the general framework of, let's say, the program that you will have then to modify. Okay, so I will also send an email about this to everybody. And so please bring your, next Friday, bring your laptop. Okay, so bring your PC because the final part you will have the possibility to already test something hands-on. And also about the groups, so I see that there was still activity on the doodle. At this point, it's better that I don't close the doodle until next week. So you have until next week to arrange people. If somebody is alone or is looking for other members, maybe you can contact some other students. And then next week we will try to finalize groups. So now I would like to go on with this IP address lookup algorithm. Here you have, so we have studied until the level compression try. Then there are other two algorithms, Lulea and the 3-bit map. If you want to look at them, is good, but since they are very complicated and conceptually not so different from the other ones, we can skip them. And so the next two algorithms that we are going to discover today are those based on the binary search on prefix length and binary search on prefix ranges. And they are based on a completely different way data structures compared to the tree. Okay, so they don't use the tree as a data structure. And so let's start with binary search on prefix lengths. So the key idea is that the longest prefix matching operation is translated into a series of exact matching operations. Okay, but these exact matching operations are made by matching the incoming destination IP address with subsets of the routing table, and each subset is formed by the prefixes that have the same length. So all the prefixes with the same length are grouped into the same subset, and the matching is repeated for each subset. It's an exact matching because you are looking into prefixes of the same length, so you don't have the problem of the longest. Then once you have performed all these operations of exact matching on different classes of length, this is put together in order to find the longest prefix matching, the final result. It is put together in a way that is very efficient. The exact matching operation of a list of bits, a sequence of bits, against a set of other sequences of bits of the same length can be performed in a very efficient way by using the hash tables. I don't know if you have already seen these hash tables in other courses. Now we will not look deeply into hash tables, but just I will tell you the basic features of this technique because they are relevant for this technique, for this algorithm. And so in order to perform this hash table matching, we just have to include all the prefixes of the same length into a subtable. So each subtable contain or hi contains all the prefixes of length I. And once you have created these subtables, the exact matching operation of the, the key that is the destination IP address against each of these subtables is has a complexity of 1, because let's say on average you just need a single access to memory in order to perform this hash table comparison. So if you take all the routing table, you will have prefixes of different lengths until the longest prefix, which has length W. Each of these sub-matchings are performed on each length classes, on each length class. And so in the worst case, you will have W hash tables, so W subtables. And so the complexity, if you perform this matching in a sequence going from the longest prefix to the shortest, or vice versa, the complexity is big O of W. So you have to make W on average, W access to memory in order to find matching. And each time you only look for a specific prefix length class. However, there is something that you can do better than the linear search. So we can repeat this search on different length classes, but instead of using a linear search, we can apply a binary search technique. Okay. So this is in this picture you see the scheme that represents the trie structure. Is just a way to visualize the routing table in the way that we have already explained before. But this is just for visualization purposes. The tree data structure is not used in this specific technique. And you can see that here there are these stripes or rows, if you want, and each row corresponds to a specific length class. So you have the root, that is the shortest prefix, and then the second class is prefix length equal to 2. So, or maybe the shortest, if the root is the default routing, is the prefix of length 0. Then the first, the brown, the dark gray stripe is a prefix of length 1. Then the other one is prefix of length 2, of length 3, and so on. And here we assume that W is equal to 7. So this is the original trie structure. By the stripes we are classifying the prefixes in terms of length, and then we will perform the exact matching in each of these length classes, so in each of the stripes. But the linear search would start from the bottom, for example, and go doing all the matches that we can do until the top. So in all we will do W matches. Instead, we don't want the linear search, we want the binary search. So this is on the left, shows you the binary tree that we can use in order to perform this sequence of matches. And this makes the search operation even faster in terms of complexity. So the trick is to start from the center. It doesn't matter exactly the class, the length class that you start. It's the middle one. Then if you have an odd number of classes, is exactly the center. If you have an even number of classes, it cannot be exactly the center, but it doesn't matter. Then we start and we perform matching initially here in the middle class. Then, according to the result of this matching operation, we will jump to the other two possible, one of the two possible subsequent nodes or in the tree. So in this class or in this class. And we will do the matching again in one of the two. And then based on the result, we will jump if we were here on one of these two nodes or if we were here in one of these other two nodes. Okay, this is the concept. So now we have to fix a rule that is that tells us what to do according to the result of the matching operation. And the rule has to be binary, so a binary choice. So if we perform a matching operation, we have to take one action if we don't find any matching and another action if we find matching. Okay. So the first choice is very natural. If you perform a matching operation in a certain class, for example, let's say this class in the center, and you find matching, it's clear that it is useless to go and check matchings on the classes of shorter prefixes, because obviously this is a matching result, and so you will not have even if you have matchings in the classes of shorter length, these matching are shorter than the one that we have already found. Okay, so in this case, the natural choice is if you find a matching in the class that you are testing, jump to in this case the bottom. So it means go to the first node of higher length. Okay, so this is quite easy to understand. Then the second rule is let's say less obvious, because it says if you don't find matching, start looking into the next upper node. That means start looking for prefixes of shorter length. We are obliged to take this second rule because we say that the decision is binary. So if you find matching, go down, and so if you don't find matching, you are obliged to go up. Okay, and let's say maybe also reasonable, because if you don't find matching here, maybe you will find some other matchings in shorter prefixes. However, the real reason why we are going up is only because on the other way we are going down. So we are obliged to take a binary decision. Clearly, if you go up, and if you don't find the matching here and you go up, this doesn't guarantee that you have some matching classes on the longer classes. No? So we will have to introduce a trick in order to make this rule consistent with finding a good solution. And I will explain you the trick in a moment. So you don't need to, if you introduce this trick, actually the fact that you are going up guarantees that you don't need to go down, but we have to introduce a modification. What is the complexity of this search operation? Is log 2 W. Okay, so it's less than the linear search, and so this is why this operation is very efficient. Moreover, as I have already said, each matching operation needs only one access to the memory. Actually, this is not true in general. When you are performing matching using the hash tables, you have let's say the average number of matching that is close to the average complexity that is close to big O of 1. So on average, you need only one access to the memory most of the times. But sometimes you also need more than one access to memory, and I'm going to explain you why. The hash tables are basically a technique which allows you to take a set of possible values and put them in a table, and then take an entry value, and by arithmetic transformation, you can convert this entry value into a key to search in the set of stored values. Okay, and so this is how it works. Here you have this set of entry values, and when you apply this transformation, you transform the entry value, that in our case is the part of the address of the destination address that is taken from the packet, only the portion that has the length identical to the length of the prefixes that we are considering in that specific matching. So using this transformation, you can take these bits and they are converted into the address that you have to do to use in order to access into this table. And in this table you have the hash values corresponding to all the prefixes of that specific length. Okay. With this operation, when you are mapping the prefixes of a specific length on this hash table, most of the times you can map a specific prefix on a single entry of this table. But in some cases, some prefixes collide on the same entry. Okay? So in that case, an entry of this table does not correspond to a single prefix, a single value, but to a set of values. So when you have this collision, then you have to attach to the entry of the table a list where you list all the values that are matching with that are mapped on that specific entry. So it happens that when you do the search operation, let's say you are searching for these, you are matching this destination IP address with all the prefixes, in this case of length 5. Here you have 1, 2, 3, 4, 5 right bits. So you take the first 5 bits of the destination address, and by using the hash functions, you convert them into an address. And it may be that the result of this hashing function gives you an address to a cell, a position of the array where you find a single prefix. So in this case, you will find directly the result of this matching operation. Okay, and this is just one access to the memory, because the conversion of the initial values into the address is, say, doesn't require any access to memory, is something that is can be coded into a simple mathematical operation. And then you have to access the memory to read the content, and you have directly the result. It may be that the result of this hashing function gets you to a position in the array where you don't have a single value, but you have the chain. Okay, the chain of values. These are all prefixes that are matching, that have collided into the same position after the the hash function transformation. So in this case, you have to start a linear search into the list until you find the matching value that, for example, is this one. Okay. So the complexity of the operation is a single access, so a big O of 1, most of the times. In some cases, it can be equal to a linear search, so it can be O of this NL, that is the number of the maximum number of prefixes that can collide on the same position of the hashing table. Okay? So this is basically what we need to know about prefixes. The functions to use in order to perform these transformations is not relevant for us. Okay, we don't get into the details of the specific matching functions. So let's instead look at the sequence of searches that you have to do when you have a certain number of classes. Okay, so here this figure represents the classes. In this case, we have 7 classes that corresponds to this routing table. So you have, for example, here we start from a class of length 1 because we have P4 and P5, which are length 1, prefixes of length 1. Then we have length 2, which is this P1. Then length 3, P2. Nothing on length 4, length 5, P3, nothing on length 7, and length 6 and length 7 is P8. Okay, so the first procedure is to classify all the prefixes and to put them in this structure where you have this array of pointers, and each pointer is connected to the set of prefixes of the same length, corresponding to the number that is written in the array. Then we start doing the search operation, and we apply the binary search technique. So we start from the center, and for example, here in this case, the center is class of length 4. And here in class of length 4, we find no matching. So according to the rules that we have specified to take the binary decision, now we have to jump onto classes of shorter length. And in the binary tree, the next node that we have to visit is in the middle, so it will be the node corresponding to class of length number 2. Okay? The destination address that we are checking is this one below, 11001 and so on. So in class number 2, we don't find any matching, so we have to jump again to the next node in the shorter sense, shorter direction, and the last node is 1, and here in class number 1 we find exact matching only with P4. So the result is P4. Okay. So clearly you see that this is the wrong result for this matching, because here we have 11001 that should match with P3. That should be the longest prefix matching result. So this is why we have to introduce this trick in order to make the decision regarding the no matching operation consistent with finding a good result. And the trick is to introduce extra entries that are not originally included in the routing table. They don't modify any routing decision, but they sort of drive this path on the binary search tree, so that then we find the correct solution. And these extra entries are called markers. Okay, so here we start again with the same example. Actually, this example is the same as before, except for the fact that here another entry was introduced in the original routing table, which is this P7, okay, which has this it is 10000. Okay. I am using this because it's the same that you find, the same example that you find in the book that was suggested by Jonathan Chow. So then you find the same. You can also read in the book the full description. So this is now the new set of entries. We have the again 7 classes. Now in class number 4 we have this P6. Then we still have P4 and P5, P1 and P2. Also P6 was introduced, P6 and P7. Okay, so P6 is here and P7 is here. Okay. We have to introduce, these are only the original entries that you find in the routing tables, nothing more. Now we have to introduce these markers, and these are the markers that we need. Basically, when you consider, for example, this entry in P3, this is 11001 star, and if you are not finding any matching in previous checks while you are traveling along the binary tree, the binary search tree, then you will never fall here, because if you don't find any matching, you go towards the shorter classes, so you will never arrive to this class. So the trick is to introduce the marker for this class into a class that has been visited before. This marker is only the shorter version of P3. So you take P3, that is 11001, and you shorten it to the size of 4, which is the size of this class, that will be 1100. Okay. So what happens, and the same is done here for this entry P2. We introduce the marker in class 2, that is 11. P2 that shorted to class 2. So what happens in the same example as before, the same destination address? We start searching in the central node, and here now we find the match, that is 1100. So instead of going to the left, we have to go to the right. Go to the right, we arrive here in the next node of the binary tree, that is number 6. Here we don't find any matching, so we have to go to the left. And finally here we arrive to class 5, and we find the matching. And in this case, this is the result, the correct result of the longest prefix matching operation. Okay. So we have introduced this marker here. It doesn't modify any routing on any lookup operation, because the entry is already present here. You just repeat it in a shortened version. Okay. And the same for this example, 11101. So if you start here, you don't find any matching in the central node. So you have to go to the left. Here in class number 2, if you don't insert the marker, you don't find any matching, and you go to class number 1, and then you find a matching there, but that is not the longest prefix solution. Instead, if you introduce here the marker 11, we find matching, so we have to go to the right side, and we fall in the node of class 3, and here we find the correct solution. Okay. Where to we have to introduce the matching, the markers. We don't need to introduce the markers in any class. For example, if you take this P3, you have always to consider the binary searching tree. So the binary search tree that arrives here. Here it has a leaf. Okay, ancestor node would be here, and then the ancestor node would be again on the top. In order to arrive here, you have the path that it goes from the top, the central node, then to number 6, and then to here. You have just to insert the markers only in the nodes that are preceding this specific node and that are relevant. So in this case, the searching tree is done like that. That is a binary searching tree. This is class 4. Okay. This is class 5. This is class 6. And here we have this entry that is 11001. So the question is where to put markers for this specific entry. So you start from the leaf and then you go up in the searching path. The first node that you find is this one, but here you don't need any marker because this node is on a longer class than this one. So if you don't find matching here, you will jump here in any case. Okay. Then you go up. Here you need to introduce the marker, as we have seen there. So you introduce the marker, which was 1100. Okay. And that's all, because in these other this branch of the search tree is not relevant to come here. Okay. The path to go here is only this one. Okay. And the same for the second example. In the second example, here you have 10. Sorry, here you have this is class 3, this is class 2. Here you have 111. So if you move up in the searching tree, you find this node. Here you need the marker, so you put 11. And here you don't need the marker because again it's a class of longer length. Okay, so if you don't find matching, you will go in this direction anyway. If there were some calculations of the average number of markers that is needed for a given prefix, and it results that is log w, log 2 of w. So in the worst case, when the marker is needed for the prefix of the maximum length class, you need only log 2w markers to introduce. Sometimes you don't need the marker because there is already a real entry that corresponds to an entry in the routing table, which is playing the role of a marker. For example, here you have this prefix P8, which is already in the routing table. You would need a marker in class 6 because it's the node that you have in the path of the ancestor node in this binary search path. But there is already this prefix P7 that is automatically the marker, and the same also in class P4. Okay, so sometimes the entries that you have already in the table can play the role of a marker. There is a possibility of introducing an improvement if you want to reduce the complexity of the search operation, the search algorithm. We can do what is called a prefix expansion. So in this case, we can reduce the number of matching operations that you need to do because we are reducing the number of classes. And to reduce the number of classes, we have to adopt a mapping operation of prefixes of a given length on longer classes. For example, if you take this table here, where you have 1, 2, 3, 4, 5 classes, this can be compressed on a data structure with only 3 classes. And you take, for example, P4, which is the shortest, one of the shortest prefix. You can that is of length 1. You can map it on a class of length 2 by introducing this P1. This is 1 star. So if you map it on class of length 2, you will have 1, 0 and 1, 1. Okay, you have to, in order to expand to a longer class, you have to cover all the possible combinations of the bits that you are adding. Actually, in that class, in class of length 2, there was already P1 of length 1, 0. And so in this case, you would have a collision, one value corresponding to 1, 0 is P1, and the other value is P4. But here we adopt the same strategy that we have already seen, similar to what we have already seen when we do leaf pushings, for example, for the complete binary tree. The information that remains is related to the longest prefix. Okay. So, as in terms of next hop information, P4 remains associated only to 1, 1, while here we have P1 that is capturing P4 when you look at the 1, 0. So in 1, 0, you will store the information that is coming from P1, which is the longer prefix. So the next stop is data associated to P1. So this is the final result of the expansion. Then you have to expand P3 on the second class. Here the second class is of 5 bits, so 111 is expanded in 111 00 01 10 11. So here you are adding 2 bits. It means that you have to expand it by 4 values. So we are reducing the number of classes, and therefore we are accelerating the lookup operation. The result, of course, is always the same. Okay. This is again the continuation with another example. So here we are expanding this 0 on these 2 values. Then 100 is expanded on 2 values, because from 3 we are going to 4 bits. And these classes that were originally of 6 and 7 are expanded here. P7 is expanded in these 2 values, and here we have another case of prefix capturing. P8 was already of the correct size, so P8 is longer than P7. P8 is capturing the prefix. Okay. So that is the final expansion. In this technique, you still need, however, backtracking, because sometimes the markers can lead you along the wrong path. For example, here, if the destination is 110, okay, and here we have the original hash table, the original table which contains 1, 0, 0, and 1, 1, 1. Now we have to introduce 1, 1 as a marker of 1, 1, 1. So when we are doing the matching with 1, 1, 0, we start from the center, we find matching, that is 1, 1. So we go to the bottom, we go to the longer class, and here we find no matching because we have 1, 1, 0 and 1, 1, 1. Okay. Instead, the result in this case is that we can know in advance by inspection is P1, that is the longest prefix matching. Okay. So we need backtracking because after we have visited the longest path and we don't find any matching, we have to manage this situation. We have to go back here and then try the left part, the upper part. In all these cases of misleading markers occurs when you have a set of entries in the routing table that is 0, 0, 0, 0, 0, and then a final entry that is all zeros plus 1, or a set of entries that is 1, 1, 1 of length I, with I increasing, and then the maximum length prefix that is 1, 1, 1 plus a 0. Okay. So in this case, you have to be careful because these the previous prefixes, the ones with length that is less than W, are acting as a sort of a false marker because they are pushing towards the end, but in the end we will find no matching. Okay, so in this case we need the backtrack. So this is basically all that we. This is an example taken from a real size problem. Here you see the hash tables, and we have all the classes until 32, and here we have the middle that is tested, that is 16, and then this is the next node, and then this is the next node, and so on. It's just an example of actual size. Performance of binary search, so is lookup complexity is log2 W. Take into account that you have on average one access per each classes of comparison, and we neglect the effect of the hash collisions. In that case, you will have something more than this complexity, but it occurs seldom. And then the storage complexity is n by log2 W, and this is because you need only log2 W markers that are probed instead of W markers, and so the storage complexity